I wanted to make a video for my Math 0955 students on topics that we were not able to cover in the course. And so this will be offered as bonus if you decide to do it on the final exam. So anyways, the topic is inequalities, and that's all this is going to be about. That means we're going to be looking at stuff like this. You're going to see things like A is less than B. What that means is if I were to go about drawing a number line and plotting those things on the number line, A would be somewhere, but I know for a fact that B would be to the right of it. Numbers to the left are smaller, numbers to the right are bigger. So you could, like A could be -5, B could be 10, whatever. I want to work with this inequality for a minute to show you some of the things that you can do. If I have A is less than B, then like an equation, I can add the same quantity to both sides, and all that really does is shift things to the right if C is a positive number. So wherever A was, there was A before. A plus C might be up here. But B plus C will move the same amount. And you can see that B plus C is still to the right of A plus C. You don't have to think of anything or numbers even. Just I took these numbers here and basically shifted them to the right C units. If C were negative, this would simply go to the left, but they would both go to the left the same amount. The only thing that causes an issue here is when you have something like this. If A is less than B, then I can subtract A from both sides and get that B minus A is a positive number. Well, if M is positive, then I know that a positive number times a positive number is still positive. And then let me go ahead and distribute the M through. And then I'll add MA to both sides. So the point I'm making here is when A is less than B, if I multiply by the number M, whatever it may be, as long as it's positive, the inequality is going to point in the same direction as it did before. Now, I'm using this more than anything. The 0 less than B minus A. B minus A is a positive number. Now, in the case where M is less than 0, then it's negative. M is negative, so I have a negative number times a positive number. Well, if I have a negative number times a positive number, I know that it's negative. So let me go ahead and distribute again. And I'll add MA like I did before. And you'll notice now that while it was the case that A is less than B, now if I multiply by a negative number, I see that MA is greater than MB. So the inequality switched. So that's really the only thing you need to know. For the most part, when you're working with these things, you're going to be dealing with things that are similar to equations and then trying to solve them. Let me go ahead and do some inequalities and show you. We're going to start with one variable inequalities. And so the way these will look, as my first example, you'll be asked to do something like this. Solve the inequality 3x plus 1 is greater than 5. Now, as I mentioned before, I can solve this like an equation for the most part. If I subtract 1 from each side, I get 3x is greater than 4. And then I can multiply by 1/3, a positive number, or if you would like, divide by the positive number 3, and I get x is greater than 4/3. Now, typically, what you'll be asked to do is write your answer in a couple of ways to show that you understand what this symbol means. When I write x is greater than 4/3, the answer means all numbers that are greater than 4/3. So if I go and draw a number line, this will be a graph of this, if you will. I'll locate 4/3 on the number line. So you may have 0 here, and then I'll put a hole where 4/3 would be. And this just says all numbers that are greater than 4/3. So what I'll do is I will shade the number line to go from 4/3 off to the right for eternity. And so what we have here is this little hole means that x is greater than 4/3. So 4/3 is not part of my answer. But if I take any number out here, it is a solution. Just as an example, just pick x like equal to 5. It's over here somewhere. If I were to replace x with 5, I would get 3 times 5 would be 15, plus 1 would be 16, and 16 is greater than 5. Try it with any number out here and you'll see. But this is one way that we write it. This is the graph of the solution. But we can also write it in this format where I write 4/3, comma, infinity, and I have parentheses around it. This is called the interval solution. So typically you'll get an answer like this, and then you'll have to convert to a graph and an interval. Let's try another one. Two minus 5x is less than 12. So I'll set about solving it like an equation as per usual, and I'll get negative 5x is less than 10. Now to get x by itself, this time I'm going to divide by negative 5. That means if you divide by a negative number, you have to turn this inequality symbol around, like so. Do you see it? I went from less than, now it's greater than. Over here I'll have a negative 2, and on the left I will have just x. So this is x is greater than negative 2, all the numbers that are greater than negative 2. So I'll draw a number line. This will be my graph. It doesn't matter if you put 0 on here. I really don't care if you do or not. I want to locate negative 2. And once again, I'm putting a hole there because negative 2 is not included in my answers. And then this says all the numbers that are greater than negative 2. So that means I need to shade to the right of negative 2. And once again, if you want to play around and pick some numbers in this interval to plug into the original equation, you can certainly, or inequality, you can do that. But there's the graph. And then I can also write the interval version, which notice how it mimics the graph. This certainly looks like it says negative 2 on off to the right forever. And we use a symbol infinity to recognize that it's all the numbers greater than negative 2. And once again, this is called the interval. Let's solve 2x minus 9 is less than 3x plus 4. So same thing as with an equation. I'll try to get x by itself. So the first thing I'll do is I'll try to get the x's alone on one side of this inequality symbol. So if I subtract 2x, I'll have negative 9 is less than x plus 4. And then to finish off getting x by itself, I will subtract 4 from each side, and I'll get negative 13 is less than x. So these are all the numbers that, if you will, x is any number that is greater than negative 13, or negative 13 is less than any solution. So I'll do the same thing as I did before. Let me draw my number line. And I'll put a hole where negative 13 is. And this says x is bigger than negative 13, or it says negative 13 is less than x, whatever it is. X would have to occupy the space to the right of negative 13. So there's my graph. The interval, once again, mimics the graph. And there's your two representations of the answer. Notice that on all of these, you have a range of values, not just a particular value of x, but anything greater than negative 13, if you plug it into this inequality, will work. As usual, let me go ahead and try to get my x's on one side. I'll get 3x plus 4 is less than negative 12. I'll subtract 4. I'll get 3x is less than negative 16. And then finally, when I divide by 3, being positive, I don't have to turn around the inequality. I'll get x is less than negative 16 over 3. So let me graph. And once again, I don't care where 0 is located or anything like that. Just indicate for me negative 16/3 on the number line. And then now I want x is going to be less than that number. That means x will be somewhere to the left. So all these numbers to the left of negative 16/3 are a solution. In this case, the interval version of it looks like negative infinity to negative 6/3 parenthesis. So this would be the interval version, and there's the graph. Now, if you see something like this, this is less than or equal to. So A is less than B, or A is equal to B. That's what this symbol means. That's really not much different than what we'll do. You'll see as I do an example how exactly that affects the answer. So now if I ask you to solve negative 3x minus 5 is greater than or equal to 7x minus 10, I'll still do the same game. I'll try to get x by itself over here. The only reason I'm putting x to the right is because I'm avoiding a negative coefficient for x. So that gives me 10x minus 10 on the right, and on the left I'll have negative 5. I'll add 10 to both sides of the inequality, and that tells me that 5 is greater than or equal to 10x. I will divide by 10, and I get 1/2 is greater than or equal to x. So now when you write the interval, it's no different than what you did before. If I put a 0, you don't have to, but I'll put a 0 for reference. Then I'll put a solid dot now and put a 1/2 underneath of it. Now I want 1/2 is greater than or equal to any x that I may use. That means the x values must occur to the left of 1/2 because they have to be less than or equal to it. So I'll shade to the left. And notice now the difference here is that 1/2 actually is a solution. It's not missing it as part of the answer. Now 1/2 is actually in there. If you plug 1/2 in for x, you'll get whatever you get on this side will equal whatever you get on that side. So you have the addition of one number in the solution. And the way we write the interval, once again, it mimics what we do here, except now when I get to my 1/2, I don't put a parenthesis, I put a bracket. Notice the difference there. So when you have a greater than or less than or equal, you're going to have a solid dot and you're going to have a bracket. So far, we can have any kind of answers like this. We can have a to infinity. We can have block a to infinity. We could have like negative infinity to a. Or we could have negative infinity to block a. So all of these go off to infinity or come from infinity. These are all unbounded. We can get what's called a bounded type of solution as per this next example. Suppose this time I ask you to solve 3 is less than 2x minus 7 is less than or equal to 15. What this is a compound inequality. It's two inequalities in one mathematical sentence. What it means is this. It means I have to work the inequality 3 is less than 2x minus 7 and 2x minus 7 is less than or equal to 15. Now I'll work both of these independently. So to solve this particular inequality here, I'll add 7 to both sides. And I get 10 is less than 2x. And then I'll divide by 2. And I'll get 5 is less than or equal to x. On the other hand, over here, I'm going to do exactly the same things to get x by itself. So I get 2x is less than or equal to 22. I'll divide by 2. And I'll get x is less than or equal to 11. So what you have now is what's called a bounded interval. If I draw the graph, I know that x is bigger than 5, but it's less than or equal to 11. So I'll put a hole where there's a 5. I'll put a solid dot where there's an 11. And since x is bigger than 5, but less than or equal to 11, I have no choice but to shade in between these values. And as an interval then, I could write it as 5 with a parenthesis next to it because I'm not including 5 in my answer, up to 11, but put a block next to it, or a bracket. That way I know that 11 is included, and I know that 5 is not included. Now, alternatively, let me do a redo of the same problem. We have 3 is less than 2x minus 7 is less than or equal to 15. What I can do, instead of working two separate inequalities like this, what I can do is do it all in one fell swoop, because I did the same steps to get x by itself. All I'm going to try to do then is get x by itself in the middle. And so starting that out, think about solving for x and getting it by itself. The first thing that you would do is you would add 7 to get that away. Well, I just add 7 to all three components of the inequality. And so I get 10 is less than 2x is less than or equal to 22. And now I'll do the same game. I'll divide everything by 2, and I'll get 5 is less than x is less than or equal to 11. Now this, looking at this broken solution like this in two pieces like that, I had to kind of explain that we were between 5 and 11. But here, it's pretty evident that x is between 5 and 11 just by the way this looks. It's a compound inequality, but it says that x is greater than 5. while at the same time it's less than or equal to 11. So you can do it all in one shot if you'd like. That's the way I'm going to do the next example. I'm going to do it all in one shot. So let's solve. Here we have negative 4 is less than 3 minus 8x is less than 5. So I'm going to try to play the game where I get x by itself in the middle. So to do that, the first thing I'm going to do is subtract this 3 from everything. And I get negative 7 is less than negative 8x is less than 2. Now to finish it off, I got to divide by negative 8. I think, yeah, I got to divide by negative 8. But when you divide by a negative number, just as when you're multiplying by a negative number, you need to switch the inequality. So on the left here, I'll get a positive 7/8, those negatives cancel. But now it's greater than x. And over here, it's greater than 2 over negative 8 is negative 1/4. So now on a number line, now I'm not including either the 7/8 or the negative 1/4. The orientation going from left to right is not exactly the same as here. You always have to put the smaller number first, which happens to be the negative 1/4, and the larger number second. But I will shade in between those values because x is between those numbers. And then as an interval, I recommend you do the graph before the interval because the interval will mimic the graph. And many times when you go to graph something like this, you'll know 7/8 can't come first. You know a number line allows you to orient the numbers, who's ever smaller and larger, easier than trying to get this solution. It is true that when we write these intervals, you always put the smaller number first and the larger number second. Next, we'll move on to 2 variable inequalities. That means I'll have an x and a y in them. Let me do an example to show how this works and go from there. So now you may be asked to solve something like 3x minus 5y is less than or equal to 15. The first thing that you do, let's call it step 1, I want you to graph the line 3x minus 5y equals 15. So I want you to get a graph of that. And then what we do to graph this as the same thing we normally do, I'll subtract the 3x. I'll get negative 5y equals negative 3x plus 15. And then I'll divide everything by negative 5. And that will give me y equals 3/5 x minus 3. So when you go to graph this, remember 3/5 is the slope and negative 3 tells you where the y-intercept is located at. And then to plot extra points, I'll use the slope. So the slope is positive 3/5. That means I go up 3 over to the right 5. So let me do that. Up 3, 1, 2, 3, 1, 2, 3, 4, 5. I'll run out of room if I keep going there. I might be able to go to the left though, so I'll go down 3, 1, 2, 3, and then I'll go to the left 5 units. And then I'll go ahead and put a line connecting those 3 dots. So I've got my line. Now, like before, we're going to have an infinite number of solutions. What's going to happen is this. We're either going to have solutions that are all above the line or all below the line. I have to determine which it's going to be. It's only going to be one or the other. all above or all below. I have to decide. So when we go back to the inequality, step 2, this step is to shade. And now let me go back to the original inequality. We have 3x minus 5y is less than or equal to 15. And in order to determine if I shade above or below the line, I'm going to pick a test point. Pick any point that's not on the line. If you can, 0, 0 is the best test point to use. Let me go ahead and plug 0, 0 in. So I'll replace x with 0 and y with 0. So I'll get 3 times 0 minus 5 times 0 is less than or equal to 15. I'll get 0 is less than or equal to 15. This is true. What that means is not only is 0, 0 a solution, you can plug it in and see, every single point above the line is also a solution because it's on the same side as 0. So what I do is I include shading, something like this, to indicate that all of these points above the line are solutions. Let me do another example. So just as before, step 1, let's graph the line. So I'm going to graph negative 2x plus 5y equals 20. So I'll get y by itself. I'll add 2x. I'll get 5y equals 2x plus 20. And then I'll divide by 5. So y equals 2/5 x plus 4. So there it is in slope-intercept form again. Let me get and draw that graph. This time my y-intercept is 0, 4. Let me put a dot there. And my slope is 2/5. So I will go up to right 5. So let me go up to 1, 2, and then to the right 5. 1, 2, 3, 4, 5. And I'll put a dot. Let me go in the reverse direction as well. And any more I'll go off the graph. Now, this, let me finish this line. Now, as hilariously silly as it sounds, Microsoft's OneNote program does not give me the ability to draw a dashed line. And that's what I want in this case. Let me show you the difference. If this were a greater than or equal to, I would use a solid line, but I'm not. Since it's just a greater than, we want to take away the possibility of any points on the line from being a solution. So, we don't want this graph with the solid line, we want this one over here. We still need to shade. Let me do a step 2. And once again, if I can find a point that's not on the line that's convenient, like 0, 0, I'll use it. So let's go ahead and test that. This is where I use the inequality. So we will test 0, 0, and I will plug it into this inequality here. Negative 2 times 0 plus 5 times 0 is greater than 20. What I get is 0 is greater than 20, which is false. That means that 0 is not an answer. That means that anything below the line is not an answer. So my answers must be on the other side of the line. So I will shade above the line. And that's a graph of my solution set. Let's try another one. So recall, we're going to need a dashed line when we draw our answer. Step 1, we graph the line itself. Get y by itself. 4y equals negative 5x plus 20. Divide by 4, and we get y equals negative 5/4 x plus 5. So my y-intercept is 0, 5, and my slope is negative 5/4. So here's my graph, dotted lines and all. You can see 0, 5 is the y-intercept. I'll put a dot there so you can see it. And then the slope is negative 5/4, so we go down 5, 1, 2, 3, 4, 5, and then to the right 4 to get another point. Anyways, let's shade the answer. So my second step, step 2, is to shade. And for this, once again, I'll pick a point that's not on the line. 0, 0 will be my test. And let's go back to the inequality. 5x plus 4y is less than 40. So I have, I don't know why I put a 20 and then a 40 here. We'll put a 20 here, and it will match what I'm doing. Alright, so test 0, 0. Let me plug in 0 for x and 0 for y. So I have 5 times 0 plus 4 times 0 will be less than 20. 0 is less than 20. That's true. That means 0, 0 is part of the solution set. So everything below the line is a solution. So I'll indicate that with this kind of shading. You can do more adventurous kind of shading if you want, but anything like this will indicate to me what you're doing. One last example, and this will be what happens when you can't use 0, 0 as a test point, like in this example here. We do exactly what we did before. Step 1, we would have negative 2x plus 3y equals 0. I'll add 2x to both sides, and then I'll divide by 3. Now, there's no constant term here, which means that the graph goes through the point 0, 0. If you want to, you can put a plus 0 to help you see that. And then the slope is 2/3. So let me go ahead then and graph that. And since I have greater than or equal to 0, I'm going to graph it with a solid line. So there I've got my line. Now, what do you do if you can't use 0, 0 because it's actually on the line? Well, just pick any other point if you want. I highly advise you to pick something along an axis because something will be 0 there anyways. So let me just grab, I don't know, this point over here. You can pick anything you want as long as it's not on the line. So my test point is 2, 0. So step 2 is to shade. So my test point that I'm using this time is 2, 0. Let me plug it into the original inequality. I'll have negative 2 times 2 plus 3 times 0 is greater than or equal to 0. Negative 2 times 2 is negative 4. And that's a false statement. Negative 4 is not greater than or equal to 0. So that means this test point is not part of the solutions, so the solutions are above the line. Now the last topic I want to talk about are systems of inequalities. Just like systems of equations, we have systems of inequalities, and we'll be presented with a pair of inequalities, and then we have to shade appropriately. When I say solve for these type of inequalities, I mean graph the solution set. So I have 5x minus 2y is greater than 10, And then I have x minus 3y is less than or equal to negative 6. So the first thing I'm going to do is graph both of these things, both of them together on the same graph. So let me start with the 5x minus 2y equals 10. I'll get y by itself. And then I'll divide by negative 2. So there's one line. The y-intercept is 0, negative 5, and the slope is 5/2. I'll do exactly the same thing for the other line. And then I'll divide by negative 3. Now, this first line here, I'll graph with a dashed line, just because this inequality does not have an equal underneath of it. But for the one that has a less than or equal to, I will do solid. And then for each of these, you want to try to determine if the regions that are shaded like I did the previous ones. But I'm going to do them both on the same graph. Here I've graphed both of the lines on one graph. The dashed line is right here. This is the y equals 5/2 x minus 5 line. Or if you want, the 5x minus 2y equals 10. The other one is the x minus 3y equals negative 6. Now, as before, I'm going to try to determine how to shade. So for my second step, step 2, shade. And let's go back to my inequalities. I will start with 5x minus 2y is greater than 10. And since 0, 0 is not on that line, this is the dashed line I'm talking about. 0, 0 is going to be my test point. Let's test 0, 0. I'll get 5 times 0 minus 2 times 0 is greater than 0, or 0 is greater than 0. I think that was supposed to be a 10. Let's leak that 10 in there. 0 greater than 10 is false. So what that means is for the first line here, the dashed line, this one right here, the 0 greater than 10 being false means I have to shade on the opposite side of 0, 0. So I will shade downward underneath of that line. And now for the other one, that was x minus 3y is less than or equal to negative 6. I'll test 0, 0 again. And let's see what happens. I have 0 minus 3 times 0 is less than or equal to negative 6. Or 0 is less than or equal to negative 6. That's true. So that means that the point 0, 0 is a solution for the solid line. So I shade underneath of the solid line. Now, in order to be able to tell what region is going to be the answer, what I typically do is I'll draw horizontal lines underneath of this and just go all the way and continue on. Ignore the other line as much as you possibly can when you're doing these. I know it's kind of hard, but over here, these are all solutions. Solutions. If you do as I say, you'll be able to see the solution set will be here. It'll be down in this area here. You can see these are the ones with the double hatchings. if you will. I have a cross. So the overlap is basically going to be the answer. So if I would like to highlight that, I think I'll draw in a thick shading if I can to try to illustrate that. There we are. And the dotted line will tell me that those points on that line do not count. And so I can do something like this. All of this stuff will be my solution. So this sort of notched out piece of answer is my solution set. If I do want to find this point here, you can solve the system of equations. 5x minus 2y equals 10. And the other one was x minus 3y equals negative 6. And I think probably it's really easy for me to eliminate the x's immediately by multiplying the second equation by negative 5. That leads to the following equations. 5x minus 2y equals 10, and negative 5x plus 15y equals 30. Add them together. I get 13y equals 40, and so y equals 40 over 13. Let's see if that is close. 40 over 13 is just a shade bigger than 3. If we look here, my y value is just a shade bigger than 3. Now if I want to go and find the x value, I'll eliminate the y's. Let me rewrite these. This time, to eliminate the y's, I think I'll multiply the first equation by negative 3. That way I'll get a positive 6y. And the second equation by 2. That way I'll get a negative 6y. Here's what happens to my equations then. I get negative 15x plus 6y equals negative 30. And then we have 2x minus 6y equals negative 12. Let me add these together and I'll get negative 13x equals negative 42, or x equals 42 over 13. Once again, that's a little bit bigger than 3, a little bit more bigger than 3 than the other one was. And if you look at the x here, there's x equal to 3. So this point does make sense. So there's a lot of steps here. We have to solve and put both inequalities or both lines on one graph, and then we have to shade the appropriate region. That's the gist of it. Let me do one last example to illustrate again. And I think I'll use the correct terminology this time. I actually want you to graph the solution set. And we have 2x minus 3y is greater than 9. So that's a dashed line for that. And then the other one is 3x minus 2y is greater than negative 2. So that's also dashed. So as before, in step 1, let me get the equations of the lines I'm going to graph. I'll subtract 2x. Then I'll divide by negative 3. So there's one line. Let me work the other one now. As before, I'll subtract 3x this time. And I'll divide by negative 2. And now let me go ahead and graph both of those lines on the same graph. So here are my two graphs. They're both dashed, as you can see. Right here, you can see the y-intercept of 0, 1. That's this line right here. So y equals 3 halves x plus 1 is that line there. and the other one is 2/3 x minus 3. And you can see it has a y-intercept of -3. And you can check the slopes and all that kind of stuff. Let's shade. And here, once again, I can use 0, 0 as a test point for both of the lines because neither one of them goes through that particular point. So we'll start with the first one. That was the 2x minus 3y is greater than 9. So we have the test 0, 0. The 2x minus 3y greater than 9, I'll replace with 0, 0. I'll have 2 times 0 minus 3 times 0 is greater than 9, or 0 is greater than 9. That is false. So I know that on this line right here, I need to shade away from 0, 0. So on this line right here, I need to shade underneath. So let me go ahead and do that. And once again, take my advice and do vertical lines and then horizontal lines so that you can keep track of the answer. Ignore the other line while you're doing this, because if you don't, you'll get it all screwed up. So especially when they get close together like that, I have to remember which line I'm shading underneath of. Now, for the other line, where did it go? 3x minus 2y is greater than -2. So we had 3x, was it 3x? 3x minus 2y. Is greater than -2. I'll replace x and y with 0. Here I get 0 is greater than -2, and that now is true. So that means that 0, 0 is a solution for this other line. So I have to shade below that line. So what I'll do is I will do horizontal shadings this time. And then I'm just going to look for where I see the double hatching. That will be my solution set. And right here, I'm kind of this. I got to remember which line I'm actually working with here. And now we can visually see what it is. Let me go ahead and put in some yellow shading. Here, the way it worked is we went down along here, there, and then we went along this line here. And then all this stuff underneath of here. Where is that intersection point? Well, let's go ahead and find it. I'll go back to my pen, and let's go ahead. And when you find the point where they intersect, you can use the equation. So I got 2x minus 3y equals 9. And then I got 3x minus 2y equals -2. So to find that point of intersection, let me go ahead and put a dot here. I'm going to multiply the first equation by 3 and the second equation by -2. And let's see what happens. That way I'll get a 6x and a -6x. I will get 6x minus 9y equals 27. And then I'll get -6x plus 4y equals 4. And when I add these two things together, I get -5y equals 31, or y equals -31 over 5. So this point here has -31 over 5 for the y value. Now for the x value, let me get my equations again. This time I'll multiply the first equation by a positive 2. That'll give me a negative 6y, and then the second equation by a negative 3. That way it'll give me a positive 6y in the second equation. So I get 4x minus 6y equals 18, and then I get negative 9x plus 6y equals 6. So let me go ahead and add these two things together. I'll get negative 5x equals 24, or x equals negative 24 over 5. So let me go ahead and put that over here, negative 24 over 5. And I'll just check to make sure this all agrees with what I did. Negative 24 over 5 is just a shade less negative than negative 5. So my x value is close to negative 5. If you look at negative 5 for the x, and if I go down, the dot is a little bit to the right of that. Now negative 31 over 5 is just a shade more negative than negative 6. And if I go down to y equals negative 6 and then go across, you see the point is slightly under there. So this intersection point does make sense. So that is all I'm going to require you to do for these things. I don't know how many bonus points there will be, but there will be a lot of them. And there'll be an extra section on the end of the final exam where you'll have these problems to work.